I'm going to give you both of them, all right? So if you take a look at the correlate, if you have two variables, for instance, if we have x and y, and they may not be statistically independent, then the correlation coefficient is going to be equal to sigma x squared plus, and actually what I should do is put down the coefficients. Hold on a second. I'm doing this in a very basic way, but let me do it this way. Let's assume we have some equation z, and then say is equal to x, or ax plus by. All right, that's the general form of equation. A and B can be positive or negative, all right? Then you're going to find out that rho of xy is going to be equal to a squared sigma x squared plus b squared sigma y squared. Do y'all remember that part? Right. Now, if they were uncorrelated, right, I should say, I'm putting down this. I should do it this way, I'm sorry, sigma z squared. I want to do it this way, all right, because we're going to assume that we're going to get a correlation coefficient. We have an equation. This is the real way to do this. The equation is key in this one, all right? And then you're going to have plus 2a times b sigma x sigma y rho of xy. Now you can rearrange this. I like to do it this way, though. You can rearrange this so you can get rho of xy by itself. This is 1, and you'll notice the nice thing about this, there's no mean value. Can everybody see that? The mean value of either x or y doesn't appear here. But there is an equation that relates x to y, or I should say to a third variable. Then, the other way to do it is rho of xy is equal to the expected value of x times y minus x bar y bar over, and then if you remember this, it's going to be equal to 2 sigma x sigma y. Do y'all remember that?
Is it not just sigma x, sigma y?
In the book, it's listed as sigma x, sigma y.
I'm very sorry. You're right about that. I'm thinking about rearranging this, but it's. I think what I put up is right, and yeah, I'm sorry. It's just sigma x, sigma y. I'm sorry. It's absolutely right on this one.
Well, because I was gonna say I was reworking 344 last night, and I think in class the other day you'd gotten a different answer than the one the solution manual had. I think it's because you had 2 on the bottom.
Did I?
Yeah.
Why don't we do that one just to clear it up? Okay. And by the way, I'm sorry about that. This is correct. But the way all these things, the way you get these things is, if you look at the fundamental definition, they use the covariance actually to get this. If you do that, then you can't go wrong. If you want, I don't think I have to go that far back, but that's the way I would do these. And I'm very sorry about that. The reason I do that is I look at this and sometimes I'm just moving too quick. This is the one I use most of the time for everything, and the only reason I'm doing this, if there is a relationship between x and y, because this right here, this, I gotta be careful about this. If they are statistically dependent on one another, then this can be a large equation right here. If you know what I mean. Suppose you had something like 5x plus 7y, and they were correlated. Then that expected value gets to be huge. You remember some of these things where we got all these terms in there? And this one, I don't believe is that bad in general. But okay, so this is 3-4.4.
Yes.
All right, can you tell me what it is?
It was you were given w is equal to x plus y plus z.
Okay.
And then you're
plus z.
yes, and then you were given that all of their variances were 1.
Oh yeah. Sigma x equals sigma y equals sigma z equal 1, and the means are all 0?
Yes, and then the correlation coefficient of x, y is 0.
Rho of xy equals 0. Rho of y,
X.
or is xz?
Yeah, it was 1/2. And
It's
then
1/2,
y
and
is
rho
negative.
of yz What's he want?
You were first asked to find the variance in W.
And, we'll do it quickly, but if you want a variance in this, since all these are zero mean, I'm just gonna say this. W bar right here has to be zero because they're additive. If you take the mean value of those, it's the mean value of X plus mean value of Y plus mean value of Z. I'll slow down. Does everybody agree with that, by the way? That shouldn't be a problem to see. The next part is when they want, they actually want sigma W squared, right?
Yes.
And because it's the variance of W, because the actual mean values are all zero of this, that is in fact equal to just W squared bar. It would be this, it would be the actual variance of W, the second moment of W. And if you do that, that's the expected value. We can do this, but I think you know this one right here. W plus X plus Y squared, right? So that's the expected value. I'm going to just do it this way. If I look at this squaring operation, I know I'm going to have
It's X plus Y plus Z.
plus X plus Y plus Z. I'll put Z right here. Now I'll put X plus Y plus Z right here. So if I square those, I get the expected value of X squared plus the expected value of Y squared plus the expected value of Z squared. And then when you take X and multiply it, X by Y and X by Z, then you get plus XY plus XZ, and then you get plus YX plus YZ plus, and then it's going to be XZ, and at the end of the day, when you do this, you're going to get the expected value of X squared plus Y squared plus Z squared plus 2XY plus 2XZ plus 2YZ. Now, I'm just going through that kind of fast, but y'all follow me on this? If you do it right, all these, because they're just additive right here, the expected value of X squared can be added to the expected value of Y squared and so forth. Now, each one of those has a variance of 1, right? Or the expected value of X squared is Y squared is Z squared, so it's 1 plus 1 plus 1. And I'll put it down, 1 plus 1 plus 1 plus. Now here, their X and Y are uncorrelated, I believe, yeah. So that means the expected value of 2XY is 0. If you can look over there, if this is 0, right, it's going to be 0, and that means the expected value of X times Y is 0, because it has to be, in order for that to be, I know I'm moving a little fast, but how many understand what I'm doing right here? Without, I'll slow down if I have any problem. This part is going to be 2 times, and if you look at the expected value of XZ right here, maybe I should write it down like this. The expected value of XY on this one is going to be equal to 2 sigma X sigma Y times, I'm sorry, not 2, just sigma X sigma Y times rho XY, and it's going to be plus X bar times Y bar. Now for this, if it's going to be for XZ here, then I know X bar and Y bar is 0 for, right? I mean, it would be actually X bar and Z bar. This is going to be 0, so I simply take 1 times 1 times plus a half, right? So that, isn't that, y'all follow me?
That was the 0.
That was the 0.
Pardon?
X, Y is the 0.
Well, I should say XZ here, but this
So
would-
yeah, that was one.
and this would be okay, these go away, And that means this is going to be 1/2. That's what, I guess, what, this is gonna be 1/2 for this first one. Then it's plus for the same thing here, but there's going to be 2 times minus 1/2, and that means these two cancel, correct? So that's 3 for the actual sigma of, or the standard deviation, or sorry, the variance of W. That's what I'm saying. What was the second?
It asks for the correlation coefficient of W and X.
All right, that's one where you have to do the multiplication. And you all with me on this? Because now, and I'm going to just put it right here. So the expected value, I'll do this. So rho of W and X would be equal to the expected value of WX. Now, because this is going to be 0, the W bar and X bar is 0, I'm not even going to put it down. It's going to be that over 1, or basically, the correlation coefficient is the expected value of W and X. Do you agree with that, first of all? Everybody, based on the fundamental math. So this is going to be equal to the expected value. And here, W.
Well, it's not 1 and 1 on the bottom.
Sorry?
Wouldn't it be sigma W and sigma X on the bottom?
Oh, I'm sorry, you're right. That was my mistake. Sigma W is going to be square root of 3, right?
Mhm.
And then sigma X is 1. I'll try to slow down. I have 3 things I want to do today, but I'm going to slow down from here on out. Try to do a better job. Y'all with me on this one? I'm sorry about this. If I'm going to do this, rho, the correlation coefficient of this is going to be 1 over the square root of 3, and then it's simply the expected value of W, which times X, or X times X plus Y plus Z here. And if I take a look at that, that's 1 over square root of 3 times the expected value of X squared plus the expected value of XY plus the expected value of XZ. And that should be 1 over the square root of 3. Here, that's 1. And then this is 0. The expected value of XY, because the correlation coefficient is 0. And finally, for this one, right here, that of XC is 1/2, so I have 1/2 is equal to,
It's just 1/2.
it has to be just 1/2, yeah. And that is going to be 3/2 right there times 1 over square root of 3. And that is square root of 3 over 2. And was that 0.866? Is that the answer?
That was right, yes.
Okay. If I made a mistake, I apologize. Are you with me on this one, class? What else?
It asks for the correlation coefficient of W and Y plus Z.
Now, you understand, the only thing you're doing is adding just a little bit more complexity to this thing, right? And again, it's going to come down to this. Now, you can, actually, I've thought about this. You could create a new variable, W plus Z. You could do it where you get that variable, and you have the correlation coefficient of that variable. You might say with the others, but technically speaking, what we want is the expected value of W, right, times Y plus Z. So that's the expected value of WY plus the expected value of WZ. Let's see what this is going to look like. That's the expected value of X plus Y plus Z times Y plus the expected value of X plus Y plus Z times Z. And we found doubling. Is this how you did it, Jacob?
Yes.
X, Y plus the expected value of Y squared plus the expected value of YZ plus the expected value of XZ, this is the long one, plus the expected value of YZ. I'm gonna try to cut to the chase on this one, plus the expected value of Z squared. I hope I didn't miss anything, but that's what we're looking for, right? If you do this, because X and Y are uncorrelated, I can kill this thing off, right? Right off the bat, I can see it. Can you see it back? Next one here, this is just one, isn't it? Do you agree with that? The next one, if you think about that, YZ has a correlation coefficient of minus a half, it should be minus a half. Do you agree with that, class? So it's gonna be really minus a half. Then the expected value of XZ plus 1/2. Expected value of YZ minus 1/2. And expected value of Z squared is 1. So I'm basically getting this, those go away. Then I have one, I got basically 2 minus a half of 3/2. Is that right, class?
Yes.
And that would be the expected value of, is that what they asked for?
Or it's over root 3.
Did I forget a,
You,
oh, here.
Sigma,
What's that?
or it's the sigma W and sigma Y plus C on the bottom.
Oh, I didn't even divide it. This is just the expected value.
Oh, yeah, sorry, that's the.
That's expected value. Then if we want a W and, what is it, Y plus Z, that would be the second variable, right? This is gonna be this value, 3/2, and then it has to be divided by 1 over sigma. The two sigmas, and one of them square root of 3, the other's 1. So it should be, unless I've done something wrong here, square root of 3 over 2, is that right? But that, is there another part to that?
That's it.
Now, the only thing they're doing with this problem is they're adding a little bit more complexity and causing it to be a little more focused than it should be to make sure this.
I was just gonna ask, so conceptually that Y plus Z thing is the same as what we're doing with, like when we call it sigma Z, and we do Z is equal to X plus Y, is it not? Like,
Yeah, well, you make
it's
another.
essentially the same thing, right?
Well, yeah, but you don't want to use Z, you want it, because Z's.
I'm just saying like
Yeah.
the other problem.
That's right.
Is
Well,
equivalent.
the only thing we're doing is creating a new variable.
Like you could have called that Y plus, you could have made a new variable.
Y
called
plus Z could
P
be
or
B.
something, or B, yeah, okay.
It could be. Anyway, that's the technique that just going through. Did you have another question? I'm sorry about that. Everybody all right with that? Now, some of that problem was just meant, in my opinion, a good bookkeeper. It's easy to get bored and see that and lose focus, and I just did, but I got 3 things to cover. The next thing I'm gonna do is, I'm gonna get into section 5, trying to keep up with this stuff, and make sure. Now this stuff, it's gonna get a little more complicated right here. I'm gonna be, slow down, try to be very attentive to every detail in this one. There are a lot of little tricks in this stuff. You almost have to do these problems to really appreciate it. Okay. So for this one, in section 3-5, what it really says, if you have a variable, Z, equals X plus Y, and this is the key thing, X and Y have to be statistically independent or this doesn't work. Now, I sketched out how this is gonna end up being a convolution. So basically, we wanna get F of Z, so F Z of Z, if you have F X of X and F Y of Y, and they're statistically independent, then technically it's the integral from minus infinity to infinity of, and you can say f of x, it doesn't matter what variable you use here, lambda, times f of y, and then it would be z minus lambda d lambda. Now that's what it is if that's a plus, and that's convolution. So the only thing I do with this is I just say it's going to be f of x of z convolved with f of y of z. Convolution is something that I hate doing. I simply take the Fourier transforms or Laplace transforms anytime I can and do partial fraction expansion and get the value. I'm going to give you a specific example. Now, anytime you have these finite duration boxcar type of functions, you can do that too, but you have to break those up into pulse functions or U of t functions, two U of t functions. And you know the Fourier transfer, the Laplace transform of a U of t function is 1 over s. Does everybody follow me on this? So you can do it that way, but I want to give you an example, and this is 3-5.5 is a problem. I'm going to get to this one first and then work backwards on some of these. And some of them can be better. There's one in here that's really complicated. So for this one, matter of fact, just so I get it right, 3-5.5, it's a problem in the back. Here, they're going to give you, and you're going to get a variable, and they're going to say that I'm going to use z, but I think it's z is x plus y, and they say x and y are statistically independent variables. Are you with me? By the way, do you all remember how we went from here to here by that drawing? I had a 2D drawing, and I had z as a constant, showed that area, you might say, you would have to integrate the density functions of x and y over to get the density functions. And when you did that, it came out to a convolution. So back to this. Here they give you f of x is, what is that?
5 to negative 5x times u of x.
These are the ones you love, by the way. They're real easy to do, and you don't have to do convolution. Now, he doesn't say that right there, but I'm going to tell you, you do not have to do convolution. And then you have fy of y equal to
2e to the negative 2y times u of y.
Now, you all know what those functions are. They're exponential decays, right? Simple exponential decays. And now you can say, without missing a b, that f of z here, of z, is just going to be the convolution of f of x convolved with f of y of y. Or, I'm sorry, I should put of z, but I'm going to make it, there's a point I'm making here. Now, that value z doesn't mean anything physically. You might as well make this a little more friendly with what you're used to. And if you wanted f, call it of z of t, equal to the convolution of f of x of t convolved with f of y of t, you're used to seeing t. When you had signals and systems, it was time related to s when you did like convolution to, and you took the transforms, Laplace transforms. Do you all remember this? You were either in the time domain or the s domain. And the fundamental truth was that if you had any f of t here, the capital F of s is simply going to be the Fourier transform of that. And f of s is equal to the integral. We always going to use this one-side Laplace transform. So the integration here starts at 0, and almost all functions you can adapt to make that are realistic. You can take the time at the beginning of the, you might say, the onset of the event, goes from f of s from here to infinity of f of t e to the minus st dt. Do you all remember that? That's the fundamental. Some of the pairings that you remember, I hope you do. If you had a delta t here, do you remember what you get for f of s? I'm reviewing this because it's very pertinent to what we're about to do.
It's one.
It has to be 1, it's flat across the band, right? Now, I mean, it basically is invariant in S, and S is equal to sigma plus j omega. If you let sigma equal 0, you basically see that the value of that doesn't change at all for any value of omega. The next one that you should know is u of t. Remember where that goes? I just said that. That's 1 over s, right? And then, if you have e to the minus at u of t, it goes to 1 over s plus a. Do you all remember that? And we can go down the road and fill the whole chart in. These are 3 of the essentials that are really useful. And there's some properties too, but these almost, well, pretty much you can do almost any problem he comes up with just these 3 transforms if you modify things correctly. So here I got these functions right here, and I'm going to just make sure that you see this clearly. I know a lot of people hate convolution. I myself don't like doing convolution if I can just do the transforms. I don't like it either. There's too many parts. There's usually 3 or 4 different regions you have to worry about for the answer having a different form because there's different overlaps. So this is going to be equal to 5 e to the minus 5t times 2 e to the minus 2t, and really u of t. That's the same exact, but they're going to be convolved in convolution. It's this convolved with 2 e to the minus 2t, and I should have a u of t inside both of these. And now y'all agree we could do that, right? We could take that and draw them out, flip one, and start shifting, and you could get the answer. It's a little bit, it's tedious. There's many steps to that. But go to the Laplace-Domain. Now f of z of s here equals, well, now you know you're going to take the transform of these and multiply them, so it's going to be 5 over s plus 5 times, I'll stop after I write this down, over s plus 2. It's multiplied. So convolution of time, I didn't do this here, but I'll just say this. If you have convolution of time, say f of t convolved with g of t, it is the same exact thing if it's go to the transform domain as f of s times g of s multiplied. Do y'all remember this? I mean, we're going to use signals and system stuff a lot in here from here on out because it's so much easier. Now, some of you, I'm going to guess, are a little rusty in this. So this will give you time, kind of fair warning to catch up with some of these tricks and stuff like this, and I'll give you enough problems and tips so it'll keep you, it'll get you sharp again. You have to be sharp with this. So if I look at this, you can see that this is equal to 10 over s plus 5 times s plus 2. Do you agree? And at that point, I'm going to ask everybody, what do we do next? I mean, I don't know the inverse transform of that right off the top of my head. I kind of do, but do you remember what we do?
Partial fraction.
Does everybody know we do partial fraction expansion about the poles? The poles are whatever makes the bottom or the denominator go to 0. Y'all follow me on this? Well, one is a pole at s plus 5, the other is s plus 2, so I get a over s plus 5 plus b over s plus 2. And I want to find out what a and b are here. Can y'all follow me? So, do you remember how you get the value of a? Do you remember?
Don't you multiply by like s plus 5 instead of s equal to -5?
That's exactly, here's what happens on this one. If we want to solve for A, we're gonna turn this pole on. We're gonna make it equal, S equal to -5. But before we do that, we multiply both sides of this equation by S plus 5, so it goes away here. Can you all see this? Then S plus 5 over here is multiplied by, and we put S equals -5. It gets rid of that. And over here, what happens is, it's called the cover-up method. You just cover up the pole on this side. And you evaluate that when S is -5. Can everybody follow me on that part? You remember doing this now? This is like very fundamental. So if it's -5, I have 10 over -5 plus 2, or 10 over -3. Do you agree with that? So it's -10 here. Plus, and when we do the exact opposite here, we cover up the S plus 2 here, and we let S equal to -2, and then you get 10/3 as the coefficient B. So it's plus 10/3 over S plus 2. Do y'all agree with me on that? How many remember doing this kind of stuff? It may be a little while. This was an easy one, I'll admit, but it really just underscores how you go about doing it. So if I take this one, and I'm gonna go from the S domain back to the time domain, and then back to the Z domain, because T and Z in my case are the same. Can you all see that this one's just gonna be -10/3, and then when I do the inverse transform of this, I get e to the -5t u of t. That's for just this first one. Can you all see it back there? This is real handy. He doesn't mention it in the book right here. He does later, but this is where it's handy. And this one becomes simply plus 10/3, and it would be e to the -2t u of t. Now I've left it in terms of t. This would be my f of z of t. And when I simply change t to z, I get that convolution. And that means f of z would be equal to, I can go ahead and put 10/3 out in front, and I'll have e to the -2z, z minus e to the -5z, and u of z. Everybody agree with that? Okay. Elijah, can you do this with me here? This is 3-5.5. See if in fact that's the answer. I believe it is. But they do it with convolution, where they flip and shift and do all that. It's a pain in the butt.
Well, they asked for like FC of 0.
What?
I think they asked for, like, they want us to plug in values.
F of z of 0.
Yeah.
Just look at that.
Yeah.
It's 0, isn't it?
Yeah.
Can you all see if this is f of z? If z is 0, I have 1 minus 1, it's 0. What else did they ask for?
The value for which FC of z is greater than 1.
What? Capital F of z. What? FC will never be greater than 1. Read that again.
The value, so for the random variable z is equal to x plus 5, find the value for which FC of z is greater than 1.
The probability, let's see.
Oh, probability of z greater than 1. Okay, sorry. I'm thinking f of z can never be greater than 1. It has to be probability of z.
What's called?
Oh, that's the third one.
It's for part B. It's the value for which FC of z is greater than 1, and then part C.
Capital F
No, it's lowercase f.
is greater than
It's,
1? Huh? F of z can be greater than 1. Capital F of z can.
Yeah.
What's that?
Yeah, I mean, it is lowercase f.
It is, well, for greater than 1, what do you do for this one? Set it equal to 1. You follow me on this? And that's kind of a stupid question, but if I look at this, I set it equal to 1, and they want the value of z, just one value?
well, it says the value, so I'm guessing one.
It's greater than 1. Well, the peak value, how do you find the peak value for that?
Derivative.
Take a derivative of z with respect to z. I don't remember this part, but take a derivative of that with respect to z. Do you agree with that? Set it equal to 0, and then evaluate it? Out of curiosity, what would that be? Forget the 10/3, take a derivative of that. You got minus 2e to the minus 2z, right? And then it's going to be equal to plus, forget the 10/3, you don't need that, plus 5 times e to the minus 5z equals 0. Let's see what happens here. I have 5e to the minus 5z. Is this going to work? Equal to 2e to the minus 2z. So you get 5e to the minus 3z equal 2. So that's going to be 2/5 equal e to the minus 3z. Gosh, natural log is about 2/5 equals minus 3z over minus 3 equals z. Is that the right answer?
Wait,
That's going to be the maximum value.
the max, sets up a inequality with, solving for z that becomes greater than 1. So he just sets
So
a,
f of z greater than 1.
yes. So he just sets in,
Something really doesn't
Inequality
sound right
and
about this
solves it.
problem. That, who cares about it? Let me just look at this book. All right, for part B, is that the value though? Is it the log? Can anybody do that for me? Log of 2/5 divided by minus 3.
0.3.
Is it 0.3? Well, this is wrong. He said for z greater than 0.454. What happens to f of z as it goes to infinity? It goes to 0. Can you all see that? That's wrong. Oh, let's see here. Wait a second. See, that's the value of z. If you take the log of 2/5, the natural log, divided by minus 3, what do you get?
It's 0.305. It's pretty close.
Yes, 0.4541.
I plugged it back into the original f of z. It's like 1.08.
All right, if you plug in 0.4541, now there is 10/3 in front of that. So we didn't actually multiply it by 10/3. It will be greater than 1 for that's going to be the maximum value. But if you plug in 10/3, what do you do? Oh, I see. Yeah, you could do that. That could be an iterative solution. In other words, what he does is he doesn't have a mathematical solution for this. He just says that z greater than 0.4541 will give you an f of z greater than 1, but who cares about that? The only thing you care about, you're using that for probability, by calculating probability of events. And then what's part here? Part C?
Probability that z is greater than 0.1.
All right, now at that point, I'm just going to say this. If this is f of z, if you integrate that from 0.1 to infinity, you get the probability it's greater than 1. Do you agree with that? Or you could take 1 minus the integral of this from 0 to 0.1, and you get the same value. Do you agree with that, class? I just wanted to make that point. The real thing,
Maybe this is a dumb question, but why didn't you include your step function when you were doing that?
it's only going to be for positive z.
Oh,
Negative z is impossible for this one because of the u and t functions.
so if you're integrating it, would you integrate with your step function and then get it,
Well, you start the integration at 0. U of z just means it's 0 for any values of z negative. So you don't even bother.
oh,
with those.
yeah.
Okay.
Oh, and since you're above 0, it doesn't matter.
Just above 0 and above, it
Yeah.
has values non-zero technically. But that's how you do it. Anyway, I'm sorry about that part of the problem. My real focus here was to just show you using basic convolution, you can set up the convolution here and then replace z with t, because that's what you're more familiar with, I think. When you do convolution, you're used to seeing t and you're used to seeing s, right? If you're doing, and the transforms make it so much easier. That's what I'm telling you. It's much easier to take Laplace transforms and multiply them and then do partial fraction expansion, then do some of these silly, some really crazy integrals you can get with convolution. I wanted to make that. The next one I wanted to do, got a lot I want to do, but the last time, if you take a look in the book, did we do 3-5.1 or not? No. Is that right?
Isn't that the one that you did using, like the actual, like
Convolution?
graphing of convolution?
Yeah, do you all remember me doing this? This is one where you had a function and you had to, well, the way I did it, I scaled one of these, yeah, take a look at this. I think it had, I scaled one of the density functions and I just did the, literally I did the boxcar integration, right? I want to tell you with that one, you can do it with Laplace transforms too. And I'm going to say this much. Oh, I better do this too with Laplace transforms. This is something you don't know. Or maybe you do know it, but it's been a while. All right, these three Laplace transforms, these pairings, are important if you're doing this. A couple other ones. If you have anything where you have, basically this, if you have f of t here goes to capital F of s, this is properties. If I have f of t minus something, you can call it minus a. I don't know if you remember this one, we can prove it if you don't. Do you remember what it goes to? Assuming you know this. It goes to e to the minus what? as times f of s. Do you remember this is a phase change? Do y'all remember? How many do? Now that's nice, believe me. And if you have, well, that's good for stars. There's another, this is a property, but if you have a pulse function, I want to just show you this because some of your books have a different, they call it a rect function. If this is from minus tau and this is tau, and this axis is t, the pulse function p tau of t, also called the rect function of t over tau. That has a transform. Do you all remember the pulse function or rect function class? This has a transform of, and this is a boxcar thing, this is real important. This simply transforms to tau times the sinc function, and now you're going to have pi tau here over 2. Do you remember this one? You remember the sinc function? You can get this, there's a variety of ways to get it, but that's what it is. Sometimes they do it as, oh, wait a second. It should be pi I'm going to do one thing here. I'll do it this way. If I have u of t minus a, that's e the minus AS divided by S. This is what I'm gonna show you. I'll do it this way. Now, if I had U of T plus A, that's gonna be E to the AS over S. Okay. Now, if you take a look at the pulse function, or P tau of T, this is going to be equal to U of T, and it's going to be, this is a T here, plus tau over 2, minus U of T minus tau over 2. And I'm just redefining it in terms of this value A here. Can y'all follow me on this one? This is a rect function, basically, with tau. Put down here. This transforms, I better do it this way. This is going to transform as 1 over S, and then you're going to get E to the AS minus E to the minus AS as such. Can you all follow me, class? Now, the reason I'm doing this is when you get pulses, these boxcar things, they'll transform it in this form. And when you multiply that times something else, a lot of times you're going to get another 1 over S plus A. Say an exponential will have a transform of 1 over S plus A, or maybe not A, but 1 over S plus B. Then when you multiply it, the poles are going to be S and 1 over S plus A. And you can separate that and very easily get the values of the partial fraction expansion and go backwards. But you have to remember this phase business right here. Because if you see a function over here that you know the inverse transform of, but it's multiplied by E to the minus AS, like E to the minus 2S or something like this, then you know, you just take that function, basically, the F of T, that corresponds to that, and you simply put a delay in there. And that makes it really easy. I don't have enough time today to do a problem with that, but I will get to it. I wanted to do one more, at least one more here, because some of these are getting more difficult in a hurry. I'm gonna get one that's not gonna be too tough. That's a tough. That's gonna take 15 minutes. One second, I will get you. It's problem of 3-5.3, I think. Yeah, that's the number. This one took about 7 or 8 pages to do. It's a pain. I mean, a real pain. And there's no easy way to do this with a Laplace transform either. That's the problem. So I'm going to do 3-5.2. This is a difficult one too. You're going to see these are they're more difficult than what we've been dealing with.
You said 352, right?
That's right.
A commuter attempts to catch the 8 a.m. train every morning, although his arrival time at the station is a random variable that is uniformly distributed between 7:55 a.m. and 8:05 a.m.
Okay, stop. Now, forget about 8 o'clock. You with me on this? Think about the difference. 5 minutes before, 5 minutes after 8 o'clock, all right? Think of that in terms of a density function. So this, we'll just call it F of C for the commuter. So the commuter arrives minus 5 minutes late, 5 minutes early, related to 8 o'clock. And the peak value here, this is gonna be, I'll call it FC of T. It doesn't matter really on this one. And this is the commuter's probability density function for being from 5 minutes late to 5 minutes after, and it's centered at 8 o'clock. We'll add 8 o'clock to the final answer. Can you all follow me on this? So that's FC of T. Now, below it, he's gonna say, now the train's arrival time, right?
Departure time.
Oh, departure, I'm sorry, departure time. What it means, it's at the station, it's gonna depart. You get the idea in a second. And I think that's from 8 to 10 minutes after 8. Okay, so now what do? Remember the magnitude, this is gonna be 1/10, right? Now it looks like this. This still has a density function of 1/10, and call this F, I don't know, leave. Can you all follow me on this? So here's the density function of the commuter arriving. Assume, get rid of the 8 o'clock. The only thing that thing does will confuse you. We'll add 8 o'clock to the final answer, right? And what do they want?
The probability density function of the time interval between the commuter's arrival at the station and the train's departure time.
All right, here's the arrival right here. I'm just gonna call it C, and here's the departure right here, and I'll call it L. Can you all see this? We could use, maybe we should use X and Y just because we're so used to those variables. And what I'll say is, the commuter here, I'm gonna associate with a variable X, and the actual train leaving a variable Y. So this is going to be, and Z is gonna be the actual difference between the commuter arriving and the train leaving. Now, you would like that to be positive. In other words, you catch the train. If it's negative, you don't catch the train. Follow me? So this is going to be C minus L. And now, you can, X minus L. Gosh. X minus L. X minus Y. One of the days. We'll have those days later. But you all follow me on this one, class? If I have that and I want to do that, that's not X plus Y. But you know what? We can jimmy it up and make it X plus Y. Here's how. Take this variable right here and flip it. The density function, all right? And we're gonna say Y prime. Now, you're gonna have to just trust me on this one. It's gonna be a minus Y. Okay. We're gonna create a variable, and the only thing I'm doing, the reason I'm doing it, the motivation for this, is now I'm gonna say Z is equal to X plus Y. Can you all follow me? That means I can use convolution, not correlation. Y'all with me? I'm trying to avoid convolution, this is the way to do it. So remember, I make this variable, it's a dummy variable, but now this dummy variable has a different density function than this. Now, I'll put it up here. If this is time right here, this function, call it Fy prime of T, is this. From 0 to minus 10 minutes, it still has a height of 10. Can you all follow me, class? You with me on this one? So, if I do that, and now I can say that if I convolve this function with this function, I'll get the answer. Do y'all follow me? So if you look at the top part, I'm going to leave that as the one that is going to be unchanging, and I'm going to plot this versus, this is going to be the dummy variable I integrate out, and this is my minus 5 to 5, 1/10, and this is going to be my f of x of tau. And then below that, now I have to take this is the nice thing about it, right? That's my fy of t. Now I have to take fy of tau, would be here, but minus tau. Y'all follow me on this? So I'm going to flip it again. It's going to look like this. This is what it would look like like the original thing. Here's 10, has a height of 110. This is versus tau. And this is f of y prime of minus tau. Now I'll explain what I'm doing. I'm just showing you, see, this is the flip of this thing. Can you all see this, class? Remember, when we do convolution, we have to flip and then we shift one, right? This is the one I'm flipping and shifting. It'll be easier than doing that one on top, because that'll get a little tricky. Sometimes you have to be a little more careful, but you should be able to see this. Do y'all agree that's flipped? That's what we originally started with, right? Now I take that, and if you look at this, this is a tau equals 0, right? So when I move it this way, this is going to be actually plus tau right here. This is going to be tau. And I'm going to move it this way. I'm going to start with t or tau equals, if you look at this, it's going to be minus 15 for the overlap. I hope you can see this. So I'm going to just shift this and make sure you can see it. This is going to be tau plus 10 sorry. Yeah. I want to just get it over this. So this is going to be tau plus 10, and this is going to be tau. Now this would be, this picture I've drawn here is for tau. Here is going to be greater than minus 15, because at minus 15, we're at minus 5. That's where the overlap begins. Can you all see this, right? I'm trying to draw this so you can see if tau right here is minus 15, we're just at the edge, and this boxcar is moving this way. I want to make sure you can see it. With me, class? Now, by the way, these can get irritating. I just want you to know this. We'll mess with Laplace in a second if I have time. But I want to just show you how to draw it out. And remember, the trick is, if I just do this, this is going to be a correlation integration, and I don't have the Laplace, the ability to go with Laplace on this one. I can do it this way, and it effectively is this. If I do this thing where I create this other variable, now it's just pure convolution. And at the end of the day, the nice thing about this is that that variable that I've created, y prime is minus y, it doesn't change the structure of this equation. It's doing the same thing, is what I should say. It's doing the same thing. So if I move here and get the overlap area, I bet you guys can see this. I'll just take a look at this. Remember, with convolution, you take these two functions, point by point, multiply, right? There and there. It's nice if it's a boxcar. Then you integrate that function. You would take this function, whatever it is, fx of tau, multiplied by this function, the fy of t minus tau, and you then multiply point by point, integrate. So when you do it, and I'll get to the point on this one, now my, call it fz here of t, not tau, will look like this. It starts at a value of you know what? It's something when I flip it. That should be minus 15. Minus 15, and I know the total width of this thing, if the width of one is 10, the other is 10, the total width is 20, so it's going to go to plus 5. And for this, if you look at these boxcars moving together, the peak value will be right at the middle, so if I write it minus 5 here, it's not going to look right to you. And this value will be simply 1/10. And I better give you a quiz. I just realized that. But I'll finish this up next time. It's an important problem. I want to tell you one other thing about this. When you see how the cross transform simplify these things, you can, because these things drive you out.